let's look at the taxonomy of the graph representation learning methods, right? And this is the taxonomy that I have come up with, and I think this has covered pretty much everything. If you look at the overall GRL techniques, you can broadly classify into 6 categories. The first one is normal dimensionality reduction techniques. We have methods which use LDA or PCA kind of approaches to reduce the dimension of the adjacency matrix. Then we have matrix factorization based approach where we use say GraRep, right, Hope, some variation of deep work, right, graph Laplacian and so on. We have large graph based approaches where we use line, right, GPNA and so on. There are approaches which use random walk based methods like deep walk, node to vec. There are approaches which use neural networks like graph convolutional network, graph sage, right, sine graph convolutional network and so on. Then we have other methods which take care of the sine graph, hypergraph, right, more of an attention approach and so on, heterogeneous graph and so on. I won't be able to cover each and every algorithm here, but I will try to cover important algorithms that are generally used. For example, I will briefly cover GraRep, Hope, line, deep walk, node to vec, and GCN and graph sage. Okay. So I will let's try to understand each category one by one. So the first one is a normal dimensional reduction technique where so we have this adjacency matrix, right. This is n cross n, and if say n is of size 1 million, then for every node you can think of a vector of size 1 million, right. So now this 1 million size vector is huge, right. So what you can do, you can simply use say PCA kind of techniques, principal component analysis kind of techniques, or LDA kind of techniques to reduce the dimensionality. If you are not aware of what is PCA, what is LDA, please go back and check. There are many beautiful materials available online. You can look at it and see, right. So the second category is more of a matrix factorization based approach where what we do, we have this adjacency matrix A, we try to factorize it into low dimension, right. Say this is n cross p, so say this is n cross n, so we map it to n cross p and p cross n where p is much lesser than n, right. And this kind of matrix factorization is used heavily in the recommendation system that we will discuss in the next chapter. Okay. And then we have random walk based approaches, deep walk and node to vec. Here the idea is that so here the idea is how do we capture a context of a node, right. So we start a random walk from a particular node and we do k hop, say we run the random walk k times, and during that random walk process we basically sample a set of nodes through which this random walk has basically the random walker has moved, right, and that defines the context of a particular node, right. And then we try to predict this context from the given node. So we will use a technique which mostly has been used in the language literature. It's called skipgram, node to vec skipgram kind of methods, and then we will see how skipgram kind of method can be useful here for getting the embedding of nodes, right. Then we have neural network approaches where we will see how simple CNN kind of approach, convolutional neural network approach can be used in case of graph, where we define, right, we basically define a neighborhood structure, and from neighborhood structure we aggregate representations into a node, and then we run some convolution operation and so on, and then pass it to the next layer and so on. We will discuss this one. And then we have algorithms for large graphs where we discuss line and other methods specifically designed for massive networks, right. So Let us look at let us look at the matrix factorization based approaches, because the first one, the dimensional reduction approach, LDA, PCA, these are normal, and let us look at matrix factorization based approaches. And so each node is represented is represented using a d-dimensional vector, where d is much lesser than the number of nodes. So essentially we would try to come up with a matrix X whose dimension is whose dimension would be mod V cross D, right. And so let's take an example. So if one needs to needs encoding neighborhood information, context matrix of a source node is a combined polynomial matrix that contains all the representation of its corresponding neighbors. Okay. Say you have, let us say you have a high dimensional matrix W, right. So the aim is to produce a low dimensional representation X, right, given the context matrix Xc. Now what is Xc? Xc can capture a context of a node. A context can be, say, a node feature or some sort of aggregated information of the neighbors and so on. So say, let us say W is A, okay, and this is, say, n cross n, as I mentioned earlier. So we will try to come up with a matrix X which would be n cross P, and Xc would be P cross n. Xc would also be n cross P. We take the transpose, and this would be P cross n, right. So this node proximity matrix factorization, what we can do, we can use, say, a singular value decomposition, SVD kind of techniques. And what SVD does, if you are aware of SVD singular value decomposition, what it does, it basically decomposes it can be a non-regular real non-rectangular real or complex matrix. It basically decomposes say A is a real or complex matrix, is decomposes A into 3 matrices U, S, V transpose, right. U and V, so U is called the left singular matrix and V would be right singular matrix, and S would be the diagonal matrix, and U and V both of them would be orthogonal. So that U transpose would be identity matrix and V transpose would also be identity matrix, right. So at the end of the day, what we will get, we will get we will decompose W into this way, where you see sigma is basically the diagonal element of S, right, and you have S, you have U and U transpose, right, left and U and UI and UIC, left and right singular vector, and then you have embeddings, right. So you essentially you run singular value decomposition, you decompose W into left singular, right singular, you take left singular say you take left singular vectors, and then we get embeddings for every vector, every node, right. It is a straightforward approach. Now let us look at another matrix factorization based approach, which is GraRep. Okay. So this is graph representation learning technique, and here the idea is that it basically uses the the Watt-to-Vec and the skipgram approach that is there in natural language. So in natural language, what happens is that, say I am a boy and you want to capture the representation of m, right. So and we define a context. Now let us say the context is 2 words before the word m and 2 words after the word m, right. Say this is W and this is W, so this is Wn, this is Wn minus 1, n plus 1 Wn plus 2 and so on. So, we will basically capture the probability of Wn minus 1 given Wn, probability of Wn plus 1 given Wn, probability of Wn plus 2 given Wn, and so on and so forth. So, in a very simple idea, so you have a normal, say a multi-layer perceptron kind of network. Your input is the representation of the central node and the output is the representation of the neighborhood node, right. And basically the idea is that you try to approximate the embedding of the output, embedding of the neighbors based on the embedding of the central node, central word, right. And we basically pass it through a projection layer and so on, the way we do multi-layer perceptron kind of technique, and we get here an embedding, right, and this is low dimensional embedding because we project it into low dimension, and this would be the embedding of the central node, the central word, right. This is the core idea. So and this is called skipgram. In skipgram you predict the embedding of the context, right, given the central node, central word, whereas there is another approach called CBOW, right. In CBOW method you basically predict the embedding of the central node given the context nodes, okay. So, this would be probability of Wn plus 1 given probability of Wn given Wn plus 1, probability of Wn given Wn minus 1, and so on and so forth, right. So, you see here in case of skipgram, right, given the probability of the central word, you predict the probability of the context words. So, there are let us say there are m context words before W, before C, m context words after C. So, you measure the probability, log probability, this is basically log likelihood, right, of the context word, m context word, m context words before C and m context words after C, right. So, you can easily write, this is log of this one, you can easily write it into this bulky multiplication, right, operation, and then we take we move log inside, we take the we convert multiplication to summation, and then we solve the problem, right, and this is skipgram. Now, if you look at GraRep, right, GraRep exactly does the same thing in a different manner. So, the idea in GraRep is that you try to capture different levels of proximity, right. Say this one, two nodes are directly linked, right, therefore they are similar, right. If you think of this one, two nodes are not directly linked, but all their neighbors are same, they are also similar. If you look at this one, A1 and A2, they are not directly linked, but if you look at the A's 2 hop neighbors and A1's 2 hop neighbors and A2's 1 hop neighbors, they are similar. If you think of this one, right, again they are not directly connected, A1 and A2, but they are similar in 2 hops. In 2 hops all the neighbors are connected, right, and so on and so forth, right. So, how do we capture? So, if you see, so all these things are example graphs highlighting the importance of capturing k-step relational information. So, an increment in k, now k is the k-step relation, right, this is k equals to 1, k equals to 2. So, an increment in k value captures an increasing global structural information of the graph relative to the particular node, right. So, probability of transition from current vector W to context vector C, right. So, these are context. So, let us say this is your current vector and this is your context vector, right. So, probability of a context vector C given the current vector with respect to k hop is essentially, I mean, you basically capture the k hop distance using the adjacency matrix. This is essentially A of adjacency matrix W comma C entry, and you multiply this k times, right. So, you multiply k, you multiply A k times, right, and then you check this W comma C entry, right, and that would be your probability. So, you basically capture this using the probability, right, not exactly probability, but it basically approximates the probability. Okay. So, what is the idea here? So, here the idea is that for a particular node W for which you want to capture the you want to measure the embedding, right, and let us say you have a context vector context node C and the corresponding context vector C. So, what you do, you maximize the similarity between that word and the context word, and you minimize the similarity between that word and the non-context words, right. So, this is the optimization function and k hop. So, let us say k equals to 2. So, for a given word, what you do here, you take a context node C, and this is the probability, and this is essentially this one, right, okay. And then you multiply this, because this is the number of shortest paths between C and W, right, and what is this? This is the, now this is sigmoid, okay, non-linearity, right, okay. So, sigmoid of W vectors, W vector and C vector. W vector is the representation of the word W, and this is the representation of the context vector C. So, you pass this through a non-linearity, right, and then through a log. So, higher this one, that would basically give higher weightage to this one, right. So, if C and W are similar, they have lots of shortest paths of size 2, right. We basically give more weightage to this one, right. At the same time, we have negative sampling, right. So, what we do here, P of kV is essentially a distribution of vectors, distribution of vertices, right. So, we sample a vertex C dash, right, which we assume to be the non-context vertex, and then we pass the same thing using a logit, right, a sigmoid activation, but this time minus, right. So, it means that we give more weightage here and less weightage here. If we maximize this, it means we maximize this component and we minimize this component, okay. So, this is the idea of GraRep, okay. So, and then we do a lot of approximations. I am not going into details of this, and then we take the derivative, because this is the objective function. We take the derivative with respect to A, then we update the values using normal gradient descent kind of approaches, right. So, we stop here. In the next lecture, we will discuss the other approaches. Thank you.